All right, in this video, we're going to look at question 4b that says to consider the rectangle, which is the product of the interval of r1 to r2 with theta 1 to theta 2 in the r theta plane. Sketch the image of this rectangle in the xy plane under the transformation x equals r cosine theta and y equals r sine theta, and compute the Jacobian j of r theta of this transformation. Okay, so I have the rectangle here in the r theta plane as r goes from r1 to r2, theta goes from theta 1 to theta 2, and our transformation t here is defined by our familiar polar coordinate equations. Okay, so let's go ahead and just see what this transformation does to the boundary of this rectangle. So to begin, we can look at this bottom edge here in pink, and here we're just holding theta constant, right? Theta is equal to theta 1. So that's just going to describe this ray that passes through the origin. And since we're restricting ourselves for r to be between r1 and r2, we're going to get the portion of this ray as we move from a distance of r1 to the origin out to a distance of r2 to the origin. Okay, so then looking at the top edge, likewise, we're holding theta constant, so that's going to give us this ray here where theta is equal to theta 2, and again we're letting r vary from r1 to r2, so we just get this portion of that ray. Now this left edge, r is held constant, so that's going to describe a circle of radius r1, and we're just going to take the portion of this circle as we let theta vary from theta 1 to theta 2, so we just get this orange circular arc. And then likewise for the right edge, we're going to get this circular arc up here. So altogether, we're going to get this, what we called a polar rectangle, right, back in section 14.3. Okay, so we're taking a genuine rectangle in the r theta plane, and then these polar coordinate equations that define this transformation maps this genuine rectangle into this polar rectangle in the xy plane. All right, so now let's go ahead and compute the Jacobian. So for that, we're now treating r and theta just as we treated u and v. So our functions x and y are in terms of r and theta now. So I'm going to take the determinant of this 2 by 2 matrix made up of the partial derivative of x with respect to r, and then the partial of x with respect to theta, and then the second row would be the r derivative of y, and the theta derivative of y. Okay, so let's go ahead and compute these. So the r derivative of x would be cos theta. The theta derivative of x would be minus r sine theta. And then the r derivative of y, that'd be sine theta. And then the theta derivative would be r cosine theta. Okay, so taking this determinant will give us r cos squared, and then minus a negative r sine squared. So that'd be plus r sine squared. And now notice if I factor out an r, there's this familiar Pythagorean identity, and this is just equal to 1, so the Jacobian then is equal to r. Okay, so what does this imply? Well, remember, the Jacobian here is this area distortion factor, and it's telling us that if I look at the differential area element in the xy plane, okay, this is equal to this Jacobian, well, technically the absolute value of it, but it's this Jacobian times the area element over here, in this case in the r theta plane. So in other words, times dr d theta. Oh, well that's then implying that the differential area element dx dy is then equal to r dr d theta. And that, of course, is a very familiar result to us. All right, so this is a nice connection to something that we've already seen. All right, well, in the next video, we will start looking at multiple integrals now with substitution. All right, see you there.